Hello, this is a teardown and failure analysis for my team's NASA HUNCH project, Project Isobot. It's the ejecting robot challenge. We're going to be doing an analysis on what caused it to fail, specifically the movement, what it succeeds at, and possible fixes that we can do before a theoretical PDR. So let me get into it. This is going to be a discussion of all the engineering choices that we made on this robot and what makes this robot unique among the competition. First of all, movement, but it's supposed to walk through a shuffler mechanism. So it's tank drive, so it would theoretically be able to turn in the sand. Reason we did shuffler is because the specific movement of this would allow for it to better climb over obstacles while still remaining oriented towards the point that it needs to be recording, as well as we wanted to put an outer skin over it made out of mylar so that the feet would be poking out and the rest would remain contained within the mylar. We're not able to get it to that in time, but that is very possible to do before a PDR. For the camera, we have a Wi-Fi enabled security camera that we bought off Amazon. We will likely be switching to a ESP32 camera, which is much lighter and doesn't require its own battery source. It is currently taped on, but there is threading at the bottom so that a cap would go on and secure it to the frame. The main frame is printed out of PETG+, so it's very impact resistant, good layer adhesion, but somewhat lacking in tensile strength. So if I get into the movement system, the entire structure is held in place by a 3mm carbon fiber rod that runs throughout the entire robot. This really adds rigidity and strength to the entire design and is very difficult to take out, but it doesn't require any screws or fasteners or anything like that. Here's the carbon fiber rod. You can see it's still holding together even without the carbon fiber rod. That's because in addition to that, we have these 3D printed clips that then latch into place. And if we open this up, we can see the main movement system. The movement system is comprised of a cam system along 36 tooth gears that then interlock with the main driver 12 tooth gear, so it's a 3-to-1 gear ratio. And so it's multiplying the torque output of the motors by 3 times. It sits right between there, so it interacts with both gears at the same time. If we take that out, it fits onto the shaft just loosely, but there's a little key notch cut into it, which then aligns with the shaft, which you can see here. Moving on, these are resin printed out of tough resin, tough 2000 resin. Inside of here we can see we have press fit inlaid 7mm bearings, which then fit onto these little nubs of these PLA printed for higher tensile strength, because these require tensile strength. Camshafts. Within these camshafts, if you can look closely, these resin printed shuffler bars have inlaid ball bearings, so 2mm actual used in ball bearings made out of steel, so that it has very low friction. It's hard to display on camera, but it takes pretty much nothing to move this piece. If I put it back together, I can show you the programming and drop initiation. We use these 2 H bridges, a red board, what's it called? A red board accelerometer to test if it has been dropped after initiation. So we just clips in there. Then this carbon fiber rod is then just shoved through the entire robot. So how this robot turns on is in the back. There are some steel nuts inlaid into a 3D printed latch that covers our kill switch, and there are 2 magnets here that hold the latch in place. We turn it on. It's kind of hard to see on camera. It's much more visible in real life. There's a red power LED in the back, so that tells us it's on. So if I simulate a drop real quick, hold on. Okay. You heard a little beep. It should be on now. So if I drop it, wait a few seconds. You can hear the motor noise. Something is not right on the internals, but it has some movement. Let me turn it off real quick. I believe it is off now. Yeah, it's off now. We can open it back up. Then movement system comes right off like this. You can see the interaction that it has inside the cam. These little PLA printed cams sit within the gear, then they're screwed together. Overuse has kind of caused the screw hole to come a little loose, so it doesn't fully thread anymore, which we can probably fix before the PDR. How we can do that is to just print the gear and the cam as one piece via resin printing, which should be pretty easy. Oh yeah, another main part is that these PETG cushioners are built so that there's a spring to it. The spring doesn't actually provide much cushion, but it does prevent scratching of the camera lens. How we can make the spring better is to print it out of TPU or lower the thickness of this. So we will probably be doing that before the PDR if we get invited. See the ball bearings again. These are screwed together using M3 screws, countersunk, because the skin was going to go on it, or skin will go on it. If we look even further, we can see in the back, this is how it's mostly held into place, is these M3 screws that hold the main chassis together. So let me just unscrew these real quick.
Probably speed this up in post-production. We use iron alloy M3
socket screws for the back, and you can see that they're inlaid within the robot so they don't jut out very much. This is because, from my experience with BattleBots, I know that any screw that is not flush with a body tends to be a problem for any movement systems or mechanics, or even are vulnerable to damage. Within these front screws, the tolerance isn't quite right. So right now it's 0.2 millimeter tolerance on all edges that meet with plastic, but I added that to the screw sockets within the CAD thinking that it would also expand outwards while printing. It didn't actually expand outwards very much, so the screw threads aren't as pliable as I would want, which will be fixed in the next iteration. So within this chassis body, you can see the changes that we've made from the CDR in early February. Here I have the old chassis, so let me grab it. You can see here, this rim is fully integrated because I switched from, this used to be a 24 to 16 gear ratio, if I'm not mistaken. Now it's the current 1 to 3 gear ratio, which means that we had to adjust all of the chassis sizes between now and the CDR. Within the actual body, you can see more press fit 7mm bearings, which hold the motors in place. I don't actually have the right Allen key, so I'm using a flathead.
It seems like fine now.
So opening this up, yeah, there you go. You can see the inside electronics. Power switch goes into Raspberry. I'm not going to open up the main body because I don't want to mess with the electronics too much. Raspberry Pi 0. There's the H-bridge motor controller, which then goes into N20 motors. But here we can show the main issue, our main failure point that I found when analyzing this robot, which is that our N20 motors were not manufactured properly, I believe. So if I turn this on, yeah, there we go. And if I drop it, give it a second. Okay, yeah, so you can hear the motor noises and you can see the shaft spinning, but they're pretty intermittent and they fail within pretty small resistance, which I was not expecting. The power switch just disconnected, so it entered failure mode. They're gonna ignore that. Here we can see how the camera is turned on. In the back there are all the controls. If I just turn it on, it'll transmit a live stream to my phone through a Wi-Fi hotspot, which again will be fixed by an ESP32. This is laser cut panel that holds the main Raspberry Pi 0 in place. Inside we are using one of these batteries, 300 milliamp hour battery pack at 7.6 volts. So a decent amount of power. We could probably downgrade battery size a little bit, especially since it's only 30 seconds and the camera doesn't require that much power either. The entire system consumes about 6 watts of power when it's fully running, just based on the calculations of the motors and the voltage that we're giving them and the amperage. But it might be more, it might be less. We don't really have a good way of testing that. So during the CDR, the criteria that our robot is able to meet is it's able to demonstrate movement through the motors, but the motors are shot. This is the main thing that I want to change before the theoretical PDR, is switching from N20 motors to N30 motors, which are slightly wider body shape, but I could probably get worm gear N20s that will then go up and we can wire them at the top. I might increase the gear ratio so that we have more torque on the on the main body, and also these lever arms have a length to them so that we can change the length of the lever arm to change how far it moves with each step, which we can adjust pretty easily. So these are all variables that we're going to be testing very soon, because we have to finish this project regardless if we get to the PDR, because I want to see it working. And also we have a local engineering design showcase that we're going to be doing. But more about this robot, you can see that the main top carriage is reinforced with 3mm carbon fiber rod. This is printed in 2 pieces. If I can actually unscrew this and show you. So it prints vertically, so to meet 3D printing design constraints, vertically like this. Then inside these carbon fiber rods that we just inlay within the plastic, and this increases the plastic strength really great, far greater than printing out of carbon fiber nylon or any of that, because the fibers are in one piece rather than chopped carbon fiber, which a lot of teams seem to be using, and it's then secured in place with the resin that surrounds the carbon fiber rod, which is in of itself very strong and virtually unbreakable. Within the back, the piece that holds the power switch together is laser cut. This main piece is laser cut as well, out of Delrin, which is a laser cuttable plastic that's easy to work with. The entire thing was originally lubricated with graphite, but then we thought better of using a conductive material as our lubricant, so now we're using synthetic oil, which is not conductive, so we don't have any shorting issues or anything like that. For our ejecting box, a bunch of our testing data is on our website. We're going to be getting as much testing data into the website as possible, but I just wanted a video teardown of our robot design process, all of this, so that you can make a good final judgment of our project. And I thank you for watching this.